let's put our standard reduction potentials to good use and calculate the electrical potential of a cell that has this overall reaction. Now, we'll have to divide these into two different electrochemical cells, one that just contains silver and silver ions and silver metal, and the other that contains copper metal and copper ions. But this is the overall reaction that would happen if we set up an electrochemical cell using these reagents. Now, we only have reduction potentials. We don't have anything with oxidation, even though copper in this case is being oxidized. When we look it up in a table, we're going to see that we just see the standard reduction potential reaction, which is, we'll write that one right down here. We'll have copper 2 plus, which is aqueous, plus 2 electrons going to copper metal. And in the table, we would notice that this has a standard reduction potential voltage of 0.342 volts. And then for the reaction that actually is reduction, we have silver going to silver metal. Now, when we look it up in a table, we'll notice that it just has this. Because it doesn't know what stoichiometry we're pairing it up with. And the standard reduction potential for that one is 0.799 volts. Now, if we want to calculate the potential of this cell that contains these two reactions, it's very simple. We just need to identify which one is the cathode and which one is the anode, and then do a subtraction. And the formula that we're going to use is just the potential of the cell, and if it's under standard conditions, it'll have the standard symbol there. If it's not, it's the same formula, just not under standard conditions. So we use cathode minus the standard potential, reduction potential of the anode. Now, you might say the anode is oxidation. How can we just use the reduction potential in an oxidation reaction? Well, that's where this negative comes in. The negative is really taking care of that. So, if we want to know the potential of this cell, we'll just identify which one's the cathode, which one's the anode, and plug those values in. And notice, this has absolutely nothing to do with the stoichiometry of any of this stuff here. It doesn't matter that this copper requires 2 silvers for the equation to balance. Nowhere in here is anything about the number of moles. None of it. Just the potential. So, we just find out which substance was reduced. We'll put that potential right here in the cathode position. So let's look up at our equation. This went from +1 down to 0. That's a reduction. This is our cathode reaction. And there, since we've identified our cathode, the other one must be the anode, because we have to have oxidation to go along with our reduction. And indeed, we can check, see this went from 0 to +2. So to calculate the potential of this cell, we're simply going to take our cathode, which is the first reaction here, and subtract our anode. So if I just do a subtraction there, I should get 0.457 volts. Simply do a subtraction of cathode minus anode. Again, no stoichiometry tricks involved in here. Even though we use 2 silvers here, we don't have to put that in, simply cathode minus anode. I'm emphasizing this a lot because it is very important. Now, you may notice that this is a positive value, and we're going to relate that to whether this reaction will go forward or not, whether it's spontaneous or not, coming up.